Welcome to Ultimate Sleep Doctor. Tonight, we'll drift into a quiet exploration of something truly remarkable. The universe whispers its secrets in patterns, in relationships, and in the very building blocks of everything around us. Tonight, we'll uncover the periodic table, a map of the elements, the fundamental ingredients of existence. Each atom holds a story, a delicate balance of energy and form. Consider the beauty in this ordered arrangement, a testament to the underlying harmony of the cosmos. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe. Let your thoughts drift. Let's begin. Long before we had computers to predict the behavior of atoms, there were brilliant minds who painstakingly observed patterns in the elements, seeking to understand the very building blocks of our world. The story of the periodic table isn't a sudden invention. It's the result of centuries of careful investigation, starting with some surprisingly astute observations made by scientists who lived quite a long time ago. It began with a German chemist named Johann Wolfgang Derberiner in the early 1800s. Derberiner noticed something rather curious while studying groups of elements, particularly those in the emerging field of stoichiometry, the quantitative relationships in chemical reactions. He was examining the properties of elements, like their weight and reactivity, and he began to group them into triads. A triad is simply a set of three elements. He identified three sets that seemed to share similar characteristics: lithium, sodium, and potassium, calcium, strontium, and barium, and magnesium, calcium, and strontium. Within each triad, the middle element had a mass roughly halfway between the masses of the other two. For example, strontium's atomic mass was approximately the average of calcium and barium. This wasn't just a random collection. Derberiner believed these triads represented a fundamental organization of elements based on their properties. He proposed that this arrangement reflected an underlying order, a kind of harmony within the elements themselves. His work was initially met with a degree of skepticism, as the concept of an underlying order in the elements was quite novel at the time. The scientific community wasn't entirely prepared for such a radical idea, but Derberiner's observations were undeniably significant, demonstrating that there were relationships between elements that were worth investigating further. The idea of grouping elements based on similar characteristics was a major step forward. However, Derberiner's approach was limited by the relatively small number of elements known at the time, and the fact that his triads were somewhat arbitrary. He didn't have the benefit of a vast dataset to confirm his observations. His work was largely forgotten for many years, but it laid the groundwork for future investigations. Several other scientists continued to explore similar patterns, but no single, widely accepted system emerged. Then, in 1869, a Russian chemist named Dmitry Mendeleev took a dramatically different approach, one that would ultimately prove far more influential. He was working on a systematic arrangement of all known elements at the time, which numbered only 63. Mendeleev wasn't simply listing elements alphabetically. He was organizing them based on their atomic weights and, more importantly, their chemical properties. He arranged the elements in order of increasing atomic weight, but he wasn't afraid to break the rules when it suited his purpose. His key innovation was recognizing that there were gaps in his table spaces where he predicted the existence of elements that hadn't yet been discovered. This was a remarkably bold move. Instead of trying to force all elements into a rigid, weight-based arrangement, Mendeleev left these gaps and boldly predicted the properties of these missing elements. For example, he predicted the existence of gallium eka-aluminum, germanium eka-silicon, and scandium eka-boron, all based purely on the repeating patterns he observed. He even predicted their properties, such as their melting points and densities, with a remarkable degree of accuracy. When these elements were finally discovered, confirming Mendeleev's predictions, it was a truly momentous occasion. Mendeleev's table wasn't perfect, of course. There were still some elements that didn't fit neatly into his arrangement, and some inconsistencies in the atomic weights of certain elements were later resolved with the discovery of isotopes, atoms of the same element with different masses. However, the sheer brilliance of his approach, coupled with his willingness to predict the existence of new elements, cemented his place as the father of the periodic table. He didn't just compile a list. He created a system that captured the fundamental relationships between elements. The table wasn't just a chart. It was a tool for understanding the behavior of matter. Mendeleev's periodic law, stating that the properties of elements are periodic functions of their atomic weights, became a cornerstone of chemistry. It wasn't just a description of the table itself, but a fundamental principle governing the organization of the elements. Mendeleev's table quickly gained widespread acceptance within the scientific community. It provided a powerful framework for understanding chemical reactions and predicting the behavior of new compounds. The discovery of these predicted elements, gallium, germanium, and scandium, provided extraordinary validation to Mendeleev's work. It showed that the periodic table wasn't just an academic exercise, but a practical tool with the power to guide scientific investigation. The scientific community slowly began to move beyond the limitations of simply arranging elements by atomic weight. The realization that atomic weight was not the fundamental organizing principle, but rather a consequence of the underlying arrangement, became increasingly clear. Mendeleev's table, with its emphasis on repeating patterns and predictive power, revolutionized chemistry, laying the foundation for the modern understanding of atomic structure and the behavior of matter. It's a remarkable story of observation, intuition, and the power of a well-crafted system to unlock the secrets of the world around us. It continues to evolve and expand as new elements are discovered and our understanding of atomic structure deepens. But it all started with the insightful work of Derber-Reiner and the bold, visionary efforts of Mendeleev. The periodic table, as we've come to know it, is a remarkably elegant arrangement of all the known elements. But what truly governs this arrangement? It wasn't simply the properties of the elements themselves, their reactivity, melting points, or colors, that guided Dmitri Mendeleev's initial work. Instead, the key to unlocking the table's order lies in a fundamental property of every atom, its atomic number. The atomic number is a single whole number that represents the number of protons residing within an atom's nucleus. Protons are, as you know, positively charged particles and are absolutely essential to an atom's identity. The number of protons defines what element an atom is. An atom of hydrogen, for example, always has one proton. An atom of helium always has two. Lithium has 3, beryllium 4, and so on. This number is constant for a given element. It never changes. Mendeleev initially based his table on arranging elements primarily by their chemical properties. He noticed that elements with similar behavior often appeared together, forming vertical columns. However, he also recognized a recurring pattern. Elements in the same column tended to have similar atomic weights. This was a clever observation, but it wasn't without its inconsistencies. He had to leave gaps in his table, suggesting the existence of undiscovered elements that would eventually fill those spaces with properties matching their predicted positions. This predictive power was a cornerstone of his genius. However, a brilliant young physicist named Henry Moseley, in the early 20th century, revolutionized our understanding. Moseley was studying the spectra of X-rays emitted by elements. He discovered a direct relationship between the wavelength of these X-rays and the atomic number of the element. Specifically, he found that the wavelength decreased as the atomic number increased. He realized that atomic number wasn't simply a count of protons. It was intrinsically linked to the atom's fundamental energy level. The atomic number directly influences the arrangement of electrons orbiting the nucleus. Electrons are negatively charged and, due to their quantum mechanical nature, don't simply orbit in neat circles. Instead, they occupy specific energy levels or shells. The greater the atomic number, the more energy levels an atom can accommodate. Each energy level can hold a maximum number of electrons, and this capacity increases with the atomic number. This increased electron capacity profoundly affects an element's chemical behavior. Elements with higher atomic numbers have more electrons available for bonding. The outermost electrons, called valence electrons, are the ones involved in forming chemical bonds with other atoms. The number and arrangement of these valence electrons dictate how an element will react, how it will interact with other substances, and ultimately its place within the periodic table. The periodic table, therefore, isn't just an alphabetical list or a table sorted by atomic weight. It's organized by atomic number, and this provides a much more accurate and fundamental basis for understanding the relationships between elements. The table's rows, called periods, correspond to the filling of electron shells. As you move across a period, electrons are progressively added to the outermost shell, leading to predictable changes in chemical properties. The table's columns, called groups, are defined by elements that share the same number of valence electrons. This shared arrangement dictates their similar chemical behaviors. For instance, all alkali metals, group 1, have one valence electron, which they readily lose to form positive ions. Similarly, all halogens, group 17, have 7 valence electrons and tend to gain 1 electron to achieve a stable configuration. The discovery of isotopes, atoms of the same element with different numbers of neutrons, adds another layer of complexity. While the number of protons defines the element, the number of neutrons can vary, leading to different isotopes of the same element. However, the atomic number, that single, unwavering number of protons, remains the same for all isotopes of an element. Modern periodic tables now often display atomic numbers alongside atomic weights. Atomic weight is a more precise measure of an element's average atomic mass, taking into account the abundance of its various isotopes. Yet, the atomic number remains the most fundamental and crucial characteristic, the defining feature that places each element in its correct location and reveals the underlying order of the universe. It's a testament to how deeply connected the properties of matter are to the very building blocks of existence, the protons within the nucleus of every atom. The periodic table, built upon the concept of atomic number, is more than just a chart. It's a map of the elements, a visual representation of the fundamental forces that govern their interactions and their place within the grand scheme of chemistry and physics. It's a beautiful and powerful tool, born from careful observation and groundbreaking scientific discovery, and it continues to be at the heart of our understanding of the world around us. The early attempts to truly organize the growing list of known elements weren't quite as intuitive as Mendeleev's later approach, but they were incredibly important stepping stones. After the work of chemists like Derberiner and Newlands, a prevailing thought was that there must be a discernible order to the elements, driven by some underlying property. The most obvious way to begin was simply to arrange them in order of their atomic weights, the weight of a single atom of the element. It seemed logical. If elements shared similar characteristics, it was reasonable to assume this similarity was linked to their mass. The concept was remarkably simple, and chemists, particularly in Germany, enthusiastically pursued it. Several German scientists, notably Robert Bunsen and Julius Lothar Meyer, independently arrived at remarkably similar arrangements of the elements based solely on atomic weights. Bunsen, a brilliant experimentalist, meticulously measured the characteristic colors of flames produced when elements were heated, a technique he called spectroscopy. These spectral fingerprints proved immensely useful in identifying elements and helped refine measurements of atomic weights. Mayer, a meticulous chemist and mathematician, compiled a comprehensive table of elements arranged by atomic weight, meticulously documenting his findings and illustrating his table with precise diagrams. His table, published in 1864, was remarkably similar to Mendeleev's, and the two scientists initially regarded each other with considerable respect. However, the increasing number of elements presented immediate and significant challenges. The measurements of atomic weights themselves weren't always precise. Early methods for determining atomic weights were often imprecise, relying on techniques like the combustion curve, observing the temperature changes during a chemical reaction. These methods weren't consistently accurate, and as more elements were added to the table, discrepancies began to appear. Some elements seemed to fit neatly into the proposed order, but others didn't. For instance, Elements like beryllium and magnesium appeared to belong in one group, yet their properties didn't consistently align with the expectations based solely on their positions. Furthermore, the simple arrangement by atomic weight didn't always predict the properties of undiscovered elements. This was where the system started to falter. The periodic law, as we understand it, dictates that properties of elements should repeat periodically as the atomic weight increases. But if the only factor guiding the arrangement was atomic weight, it couldn't account for the occasional breaks in this repeating pattern. Scientists began to suspect that atomic weight alone wasn't the sole determinant of an element's characteristics. The system was producing an order, but it wasn't a perfectly predictive one. The problem intensified as the table grew. The existing elements, while numerous, weren't enough to fully explain the observed patterns. The gaps in the table, those spaces left deliberately by Mendeleev, weren't just absences. They represented educated guesses based on the observed relationships between an element's properties and its position in the table. However, with a smaller number of elements, these gaps were largely theoretical. The system couldn't consistently predict the properties of elements that hadn't yet been discovered. The very act of filling in the gaps with hypothetical elements, based on their assumed positions, demonstrated the system's limitations when considered purely in terms of atomic weight. Another difficulty arose because the method for determining atomic weight was not entirely reliable. Different measurement techniques yielded slightly different values for the same element. This variation, although seemingly minor, when applied across a long list of elements, introduced considerable uncertainty into the arrangement. The system was vulnerable to the inaccuracies in the measurements. The differences in atomic weights, coupled with the inherent imprecision of the measurement techniques, meant that an element's position in the table could shift depending on the atomic weight measurement used. Moreover, the arrangement solely based on atomic weight didn't account for the wide range of properties observed within a group of elements. For example, elements in the same group might have similar chemical behavior, but their physical properties, like melting point or density, could vary considerably. The atomic weight ordering simply didn't explain this variation. It was as if the system was prioritizing one aspect of an element's behavior, its chemical reactivity, without fully considering the other aspects. The limitations of the purely atomic weight-based system became increasingly apparent as more and more elements were identified. It was clear that a more sophisticated approach was needed, one that could account for both the observed chemical properties and the underlying relationships between those properties and the elemental composition. The early attempts at organizing the table by atomic weight were crucial in establishing the concept of periodicity, but they ultimately proved insufficient for accurately predicting and explaining the vast diversity of the elements. The groundwork had been laid, but a new, more fundamental principle was required to truly unlock the secrets of the periodic table. The late 19th century was a time of incredible scientific exploration, a period where scientists were starting to peel back the layers of the universe and understand the fundamental building blocks of matter. while Dmitri Mendeleev's periodic table, established in 1869, provided a remarkably effective framework for organizing known elements based on their properties. It wasn't complete. There were gaps, inconsistencies, and a growing suspicion that certain elements might behave in ways that didn't neatly fit into his system. This suspicion centered primarily around the work of several brilliant chemists, most notably Lord Rayleigh and Sir William Ramsay. Their investigations into the properties of gases were about to dramatically reshape our understanding of the table and introduce a new category of elements, the noble gases. Initially, scientists had assumed that all gases were capable of reacting, that every atom possessed a hunger for interaction. This belief stemmed from the prevailing understanding of chemical bonds and reactions. However, Ramsay, a Scottish chemist working at the University of London, was meticulously examining the properties of gases produced by analyzing air trapped in porous jars. He wasn't simply observing that gases existed. He was painstakingly characterizing them, measuring their densities, their refractive indices, and, crucially, their ionization potentials. These measurements revealed some truly perplexing behavior. He and his assistant, Morris Travers, were studying the decomposition of liquefied air, a process that involved heating the liquid to extremely low temperatures. As they carefully collected and analyzed the gases released, they discovered two new substances, helium and neon. The discovery of helium was a particularly surprising one. Ramsay and Travers had isolated it from mineral deposits, specifically from the ancient, solidified lava flows of Crete, a place they affectionately called Helvetia, Switzerland's old name. The gas was remarkably inert, meaning it resisted chemical reaction, a characteristic unlike anything they had previously encountered. Its density was significantly less than that of air, and its spectrum, the pattern of light it absorbed and emitted, was exceptionally sharp and clean, indicating a highly stable electronic configuration. It was as if this gas simply refused to interact with the world around it. Following the successful isolation of helium, Ramsay and Travers continued their investigations, focusing on other air-extracted gases. They meticulously analyzed the components of air collected in jars exposed to varying temperatures. Their most significant discovery came in 1898, when they dramatically expanded the known list of inert gases. They discovered neon, argon, krypton, and xenon, all trapped within incandescent light bulbs, a fitting discovery, given the gas's unusual properties. Each of these gases possessed a unique spectrum, a distinct density, and most importantly, a stubbornly high ionization potential. This meant that it took a tremendous amount of energy to remove an electron from their atoms, a clear indication of their stability. The key to understanding their inertness lay in their electronic structure. While Mendeleev's table grouped elements based on atomic mass, Ramsay and Travers recognized that the properties of these newly discovered gases pointed towards a complete outer electron shell, 8 electrons in their atoms. This fulfilled the then-emerging concept of the octet rule, proposed by Gilbert and Lewis, which suggested that atoms tend to gain, lose, or share electrons to achieve a full outer shell of 8. The noble gases, therefore, were inherently stable because they already possessed this perfect configuration. The realization that these gases were chemically inert had profound implications. It forced scientists to reconsider the fundamental nature of chemical bonds and reactions. It demonstrated that not all atoms were driven to react, that some could exist in a state of remarkable stability. The table was no longer simply a system for organizing elements based on atomic mass. It was evolving into something far more sophisticated, reflecting a deeper understanding of the relationships between atomic structure and chemical behavior. The placement of these new elements on the periodic table presented a challenge. Initially, Ramsay and Travers proposed placing them in Group 0, formerly known as Group VIII, alongside the halogens, the highly reactive elements like chlorine and fluorine. However, this didn't quite capture the essence of their inertness. Mendeleev, always a visionary, eventually recognized the significance of this new category and added a new 8th group to the table, Group 0, specifically for the noble gases. This addition solidified the table's explanatory power and acknowledged the fundamental differences in the behavior of these remarkable elements. The discovery and inclusion of the noble gases wasn't just an addition to the periodic table. It was a paradigm shift. It dramatically expanded our understanding of the elements and their properties, and it foreshadowed many of the advancements in quantum mechanics that would later revolutionize our understanding of the atom itself. It stands as a testament to the power of meticulous observation, careful experimentation, and the willingness to challenge established ideas. The periodic table, already a remarkable achievement, continued to grow and evolve, always striving to capture the full richness and complexity of the chemical world. The periodic table, as we've begun to understand, isn't simply a list of elements arranged alphabetically or by weight. It's a map, a deeply intricate map that reveals the fundamental relationships between these building blocks of the universe. But what drives this arrangement? What secret code dictates why lithium likes to form simple salts, while francium eagerly seeks out reactions with almost anything? The answer lies in the concept of electron configuration, a surprisingly powerful idea about how electrons behave around an atom's nucleus. At the heart of an atom is the nucleus, containing positively charged protons and neutrally charged neutrons. Orbiting this nucleus, however, are the electrons. These tiny particles possessing a negative charge are responsible for an atom's chemical properties. But electrons aren't just randomly buzzing around. They follow a set of rules, a predictable dance dictated by quantum mechanics. This dance, this arrangement of electrons, is what we call electron configuration. Now, electrons aren't like tiny planets orbiting the sun. They behave more like waves existing in regions of space called orbitals. These orbitals have different shapes and energy levels. Think of it like a set of concentric shells or layers surrounding the nucleus. The first shell, closest to the nucleus, can hold a maximum of 2 electrons. The second shell can hold up to 8, and the third 4, and so on. Each shell is further divided into subshells, S, P, D, and F, each with its own distinct shape and energy level. The C subshell, for instance, is spherical, while the P subshell is dumbbell-shaped. The electron configuration describes exactly how these electrons are distributed across these shells and subshells. It's essentially a shorthand notation that tells us how many electrons are in each orbital. For example, the electron configuration for oxygen, O, is 1s 22s 22p, for this means there are 2 electrons in the 1 subshell, 2 in the 2 subshell, and 4 in the 2p subshell. But simply knowing the electron configuration doesn't tell us why oxygen reacts the way it does. It's the arrangement of electrons that determines its chemical behavior. The number of valence electrons, the electrons in the outermost shell, is particularly important. Oxygen has 6 valence electrons. This means it needs to gain 2 more electrons to achieve a stable, full outer shell, mimicking the electron configuration of noble gases, which are exceptionally stable. The periodic table then reflects this electron configuration principle. Elements in the same group, a vertical column, have the same number of valence electrons. Because they have the same number of valence electrons, they tend to exhibit similar chemical properties. Sodium, for instance, has 1 valence electron, while chlorine has 7. They both readily form compounds with each other, creating sodium chloride table salt. This similarity stems from their shared electronic structure. Moving across a period, a horizontal row reveals a different kind of trend. As you move from left to right, the number of protons in the nucleus increases, leading to an increase in the number of electrons. Consequently, the electrons are added to successively higher energy levels. This change in energy levels profoundly impacts an element's reactivity. Elements on the left side of the table, generally, are less reactive because their outermost electrons are closer to the nucleus and therefore more tightly bound. They require a significant amount of energy to lose these electrons and participate in chemical reactions. Conversely, elements on the right side, particularly those in the halogens, are incredibly reactive. They have a strong tendency to gain electrons, filling their outer shells and readily forming salts. This difference in reactivity is directly linked to the energy required to remove or add electrons, a concept beautifully illustrated by the periodic table. The further an element is from noble gases, the more energetically favorable it is for it to react and gain or lose electrons. Furthermore, the periodic table also predicts the type of bonds an element is likely to form. Elements tend to form bonds to achieve a stable electron configuration. For instance, metals like magnesium readily lose 2 electrons to form cations, while non-metals like chlorine readily gain 1 to form anions. This predictable behavior is rooted in the underlying principle of electron configuration. The periodic trends, such as electronegativity, a measure of an atom's ability to attract electrons in a chemical bond, and ionization energy, the energy required to remove an electron from an atom, are ultimately derived from the electron configuration of an element. Electronegativity increases as you move across a period because the atoms have a greater effective nuclear charge, leading to a stronger pull on electrons. Ionization energy, also generally increases across a period due to the increasing nuclear charge. It's important to remember that electron configuration is a model, an abstraction that helps us understand the behavior of atoms. Quantum mechanics provides the rigorous mathematical framework underlying this model, describing the probabilities of finding electrons in specific orbitals. Yet, the basic concept that the arrangement of electrons dictates an element's properties remains a cornerstone of chemistry. The periodic table, therefore, isn't just a list of elements. It's a powerful tool reflecting the fundamental relationship between electronic structure and chemical behavior. It's a map built on the invisible dance of electrons, guiding us to understand the intricate world of chemical reactions and the diverse properties of the materials that make up our universe. As you continue to explore the table, remember that every element's position is determined by its electron configuration, a silent but incredibly influential force shaping the very nature of matter. The early attempts to arrange all known elements didn't fully capture a fundamental property: metallic character. Scientists realized that elements weren't just defined by their atomic weight or the number of orbiting electrons, but by how readily they gave up electrons. This willingness to share electrons, to participate in chemical bonding, is what dictates how an element behaves. Some elements, like gold and silver, seem to effortlessly donate electrons, forming strong, stable bonds with others. They exhibited a remarkable tendency to become positively charged ions, readily participating in reactions where they lost electrons. Others, like sodium and potassium, displayed a different behavior, readily accepting electrons to achieve a stable configuration, becoming negatively charged ions. This difference in behavior was a crucial observation, and it began to shape the evolving understanding of the periodic table. The key to understanding this difference lay in examining the outermost electrons, those found in what's called the valence shell. These are the electrons most involved in forming chemical bonds. The number of electrons in a valence shell, and therefore the element's reactivity, is directly related to its metallic character. Elements with a few electrons in their outer shell, particularly those with one or two, tended to be highly metallic. These elements possess a strong desire to lose these electrons, eager to complete their outer shell and achieve a stable, noble gas-like configuration. As you move down a group on the table, this tendency intensified. Consider the alkali metals: lithium, sodium, potassium, and so on. These elements are at the far left of the table, and they share a very similar property. They're incredibly reactive metals. They practically yearn to relinquish one electron each, forming +1 ions. This isn't a random coincidence. The number of valence electrons remains constant as you move down the group. Lithium has just one, sodium has one, potassium has one, and so on. Because they all have the same number of electrons in their outermost shell, they all have the same fundamental drive to lose that single electron, creating a predictable and consistent metallic behavior. This predictability is precisely what allowed scientists to organize the table in a meaningful way. Moving to the right of the alkali metals, we encounter the alkaline earth metals, beryllium, magnesium, calcium, and so on. These elements also readily lose electrons, but they do so with a slightly different process. They typically lose 2 electrons, forming +2 ions. This increased desire to lose electrons correlates directly with their position in the table. The further to the right you go, the more strongly they exhibit metallic character. This is again due to the consistent number of valence electrons. Beryllium has 2, magnesium has 2, calcium has 2, and so forth. It's important to recognize that the metallic character isn't simply a matter of how many electrons an element wants to lose. The ease with which it loses them and the charge of the ion it forms are equally crucial factors. Elements like aluminum, found further to the right, lose 3 electrons to achieve a stable configuration, forming a +3 ion. This increased positive charge further amplifies its metallic behavior, contributing to its strength and conductivity. The periodic table, therefore, isn't just a chart of elements arranged by increasing atomic weight. It's a sophisticated map of reactivity, reflecting the fundamental tendency of elements to interact with electrons. The group number in this context represents a powerful predictor of metallic character. Elements within the same group share a similar valence electron configuration, leading to remarkably similar chemical behavior. The further down a group you go, the more predictable and consistent the metallic character becomes. Consider the transition metals located in the central block of the table. These elements present a more complex picture. They exhibit a greater variety of metallic behaviors, often retaining electrons from within their d orbitals in addition to their valence electrons. However, even within this group, there are trends. Elements closer to the left side of the transition metals tend to be more metallic, exhibiting a greater tendency to lose electrons, while those further to the right are less metallic. The underlying principle, however, remains. A consistent valence electron configuration strongly influences the element's metallic character. Furthermore, the metallic character isn't an absolute. It exists on a spectrum. Some elements are incredibly reactive metals, like sodium, while others, like gold and platinum, are exceptionally resistant to reacting. This difference stems from subtle variations in their electron configurations and the strength of the bonds they form. However, the overarching relationship between group number and metallic character remains a cornerstone of understanding the periodic table. The remarkable consistency observed across groups allows scientists to make accurate predictions about the behavior of elements. It's a testament to the fundamental laws governing how atoms interact with electrons, and provides a powerful tool for understanding and manipulating the world around us, from designing new alloys to predicting chemical reactions. The group number, therefore, isn't just a label. It's a key to unlocking the secrets of metallic character and the fascinating properties of the elements. The periodic table, as we've come to understand it, isn't simply a list of elements arranged alphabetically or by atomic weight. It's a map, a beautifully intricate and surprisingly ordered representation of how atoms behave. And that behavior is fundamentally dictated by the number of electrons they possess and how those electrons interact. While metals, as we explored in the last installment, readily give up electrons, a characteristic that gives them their conductivity and luster, there's another, equally important group of elements that operates in a completely different way. These are the nonmetals. Nonmetals don't easily donate electrons. Instead, they tend to resist sharing them. Their atomic structure, particularly the number of electrons in their outermost shell, creates a strong reluctance to relinquish control of those electrons. This resistance to sharing is the core of their behavior, and it's what sets them apart from the metals. It's important to remember that non-metal isn't a perfectly precise term. There's a spectrum of behavior, and some elements, like selenium, can exhibit properties of both metals and non-metals, showcasing the complexities inherent in the periodic table. Looking across the table, we begin to see a clear pattern in the distribution of non-metals. Generally, they tend to be found towards the right side, and particularly towards the upper right, although there are exceptions, such as tellurium. This isn't a random scattering. It reflects a direct correlation with the element's ability to attract electrons in a chemical bond. The more tightly an atom holds onto its electrons, the stronger its attraction for electrons from another atom becomes. Consider the halogens, located at the far right of the table. Fluorine, chlorine, bromine, iodine, and astatine are the quintessential nonmetals. They're incredibly reactive, almost desperately seeking to gain just one electron to complete their outer shell and achieve a stable, noble gas configuration. This drive is so intense that they readily form compounds with nearly every other element. Their reactivity decreases as you move down the group, but even iodine and astatine are far more reactive than the metals they often bond with. Moving slightly left of the halogens, we find the chalcogens, oxygen, sulfur, selenium, tellurium, and polonium. These elements share a similar, though less extreme, eagerness to gain electrons. Oxygen, for instance, is essential to nearly all life on Earth, forming oxides with countless metals and playing a critical role in combustion. Sulfur is found in volcanic fumes and is a vital component in many industrial processes. Selenium and tellurium, though less abundant, have important uses in semiconductors and photography. As we move further away from the halogens, the elements become progressively less reactive, and their behavior shifts. Carbon, found in the middle of the table, is arguably the most significant nonmetal, forming the backbone of all known organic molecules and underpinning the very foundation of life. Its ability to form single, double, and triple bonds gives it an astonishing versatility. Nitrogen, similarly, is a crucial component of proteins and DNA, and it exists in multiple allotropic forms, diamond and gaseous nitrogen, reflecting the diverse ways it can interact with other atoms. Phosphorus, another key nonmetal, exists in several forms, including white phosphorus, which is incredibly reactive and glows in the dark, and red phosphorus, which is far less reactive. Argon, while a noble gas, demonstrates a subtle nonmetallic character when it reacts with highly electronegative elements like fluorine or oxygen, forming compounds like xenon tetrafluoride. The distribution of nonmetals isn't entirely linear. There are some irregularities. For example, silicon, although situated above phosphorus, is a metalloid possessing characteristics of both metals and nonmetals, and its behavior is influenced by its complex electronic structure. Similarly, germanium exhibits semiconducting properties, bridging the gap between metallic and non-metallic behavior. The trends within the nonmetal group are tied to electronegativity, a measure of an atom's ability to attract electrons in a chemical bond. As you move down a group of nonmetals, electronegativity generally decreases because the outermost electrons are further from the nucleus and therefore less strongly attracted. This reduced attraction leads to weaker bonds and a diminished ability to attract electrons. Furthermore, the size of the nonmetal atom also plays a role. Larger atoms have weaker nuclear charge, making it easier for electrons to be drawn into a bond. This interplay of size and nuclear charge creates the nuanced patterns we observe across the periodic table. The fundamental differences in electron configuration, the number of valence electrons and their arrangement, are what drive the diverse behaviors of these elements, shaping their chemical reactions and determining their role in the countless processes that define our world. Understanding these distributions and the underlying principles of electronegativity and electron configuration allows us to predict and ultimately control how these fascinating elements will interact with each other, forming the building blocks of everything from the air we breathe to the computers we use. The periodic table, as we've explored, isn't just a list of elements arranged by their atomic weight. It's a map, a beautiful, intricate map revealing the fundamental relationships between matter itself. And nestled within the heart of that map, occupying the D block, lie the transition metals. They're a particularly fascinating group, exhibiting behaviors quite distinct from the elements that sit neatly on either side of them. Their properties are so varied, so remarkably different, that they've become the cornerstone of countless technologies, from the alloys in your bicycle to the powerful magnets in your headphones. What sets them apart begins with their electronic structure. Unlike the main group elements, where the outermost electron shell is typically filled with a simple number of electrons, 2 for group 1, 8 for group 18, transition metals possess partially filled d orbitals. These d orbitals, located within the 5th energy level, are significantly closer to the nucleus than the s orbitals, giving them a greater influence on the electron configuration. This proximity causes the valence electrons, the electrons involved in chemical bonding, to interact strongly with the nucleus, leading to stronger metallic bonding than you'd observe in other metals. Consequently, transition metals tend to be denser and harder than elements in other groups. Furthermore, because of the overlapping of the d orbitals and the relatively close energy levels, the electrons in transition metals don't occupy distinct, well-defined shells like you see in simpler elements. Instead, they occupy a band of energy levels. This means that multiple electrons can occupy the same d orbital, leading to a complex and often ambiguous electron configuration. Rather than saying a titanium atom has 5 electrons in its 3D orbitals, scientists often describe it as having partially filled d orbitals. This ambiguous nature is a key factor in understanding their chemical behavior. This complex electronic structure directly contributes to their most remarkable trait, the ability to exhibit variable oxidation states. Oxidation states are simply the charges an atom appears to gain when it participates in a chemical reaction. For elements like sodium or chlorine, the oxidation state is usually straightforward. Sodium always gains 1 electron, chlorine always accepts 1. But transition metals can display a whole range of oxidation states, often depending on the specific conditions of the reaction, the temperature, the presence of other elements, and the solvent used. Consider iron, for example. It commonly appears as iron Roman II, with a +2 oxidation state in rust, forming the reddish-brown compound iron, Roman II oxide. However, it can readily be found as iron Roman III, a vital component in hemoglobin, the protein in your red blood cells that carries oxygen. The ease with which iron can switch between these 2 oxidation states is a direct consequence of its partially filled d orbitals. The electrons can readily move between these different energy levels, allowing the metal to participate in a wide range of chemical reactions. Chromium is another excellent illustration. It predominantly exists as chromium, Roman III, but can be forced to adopt a chromium, Vi state under specific conditions, often involving strong oxidizing agents. Vanadium demonstrates a similar range of oxidation states, from +2 to +7, showcasing a truly remarkable flexibility in its chemical behavior. This ability to exist in multiple oxidation states is what makes transition metals so incredibly versatile in industrial applications. The variable oxidation states aren't just theoretical curiosities. They're the basis for many important chemical processes. For instance, the rusting of iron isn't simply a reaction between iron and oxygen. It's a complex series of electrochemical reactions involving iron, oxygen, and water, with iron transitioning between its +2 and +3 oxidation states. Similarly, the catalytic activity of many transition metals, their ability to speed up chemical reactions, arises from their ability to cycle between different oxidation states, facilitating electron transfer between reactants. Platinum, palladium, and rhodium are all frequently used as catalysts precisely because of this characteristic. The D-block elements, therefore, represent a departure from the simpler trends we've observed in other parts of the periodic table. Their unique electronic structure and the resultant variable oxidation states lead to a stunning diversity in their properties and behaviors. They aren't just metals, they're active participants in a dizzying array of chemical transformations, influencing everything from the color of your gemstones to the efficiency of your car's engine. Their ability to create alloys, mixtures of metals, further enhances their importance. Combining a transition metal like copper or aluminum with other metals dramatically alters their properties. Steel, for example, is an alloy of iron and carbon, designed for its strength and flexibility. Brass is an alloy of copper and zinc, prized for its resistance to corrosion. The careful manipulation of these alloys, driven by our understanding of transition metal chemistry, is a testament to the power and beauty of the periodic table. Ultimately, the transition metals demonstrate that the periodic table isn't simply a catalog of elements. It's a map of relationships, a framework for understanding the fundamental forces that govern the behavior of matter. And within that framework, the D-block elements hold a particularly captivating and crucial role. The periodic table, as we've come to understand it, is a grand arrangement, a carefully constructed map of the elements and their relationships. But it's not a completely finished map. There are areas, particularly at the bottom of the table, that were initially a bit mysterious, places where the regular patterns of the main group seem to falter. These areas, grouped together as the lanthanides and actinides, are sometimes called the inner transition metals, and they hold some truly remarkable secrets about the behavior of atoms. They sit snugly between the D-block metals and the main body of the table, occupying 8 spots, 14 lanthanides and 3 actinides, that extend the table horizontally. The story of their discovery is quite fascinating. Initially, scientists struggled to locate elements with similar properties to the rare earth metals, elements like cerium, praseodymium, and neodymium. These elements, found in small quantities within cerium ores, displayed unique magnetic and optical characteristics. Chemists began to suspect the existence of more elements with similar behavior, but they were incredibly difficult to isolate. The problem wasn't just their scarcity, it was their almost identical chemical properties, making it incredibly challenging to separate them. The breakthrough came in the late 19th century, largely thanks to the painstaking work of scientists like Carl Gustav Mosander. Mosander was investigating these rare earth elements when he noticed something extraordinary. While working with a sample of ytterbium oxide, he identified a tiny trace amount of a completely new element, terbium. Terbium was far more concentrated than any of the other rare earth elements he was studying, appearing as a distinct, almost pure substance. He named it after the Norse word terran, meaning earth, reflecting the minerals from which it was derived. This discovery established the principle of separation by fractional crystallization, a method where different elements in a mixture will crystallize out at slightly different temperatures. The process, repeated countless times with carefully controlled conditions, allowed scientists to gradually separate and identify more of these elements. It wasn't just about finding more elements. It was about recognizing that these elements weren't simply variations of the rare earth metals, but a completely new group of elements with their own distinct characteristics. The systematic identification of the lanthanides, from lanthanum, element 57, to lutetium, element 71, followed a predictable pattern based on their atomic numbers and electronic configurations. Each element displayed a slightly different set of properties, reflecting minor changes in their electron arrangements. Then came the actinides, even heavier elements with even more challenging properties to study. These elements, discovered later than the lanthanides, shared some similarities but also exhibited significant differences. They're named after the active ingredient in the Greek god of healing, Prometheus, as they were first discovered through radioactive decay, a process involving the emission of energetic particles from unstable nuclei. The actinides are largely defined by their radioactivity. Unlike most metals, they're inherently unstable, decaying over time through a series of transformations. This radioactivity isn't just a quirk, it's a fundamental property influencing their behavior. The higher the atomic number, the more unstable the nucleus becomes, leading to a cascade of alpha, beta, and gamma emissions. This instability affects their chemical properties as well. Many actinides form complex ions in solution, often exhibiting multiple oxidation states, meaning they can gain or lose electrons to achieve a more stable configuration. Interestingly, the properties of the actinides are often more influenced by their nuclear state, the specific energy level of the nucleus, rather than their electron configuration. This is because the nucleus's energy level directly impacts the stability of the atom and consequently its chemical reactivity. For example, uranium element 92 exists in multiple oxidation states, each corresponding to a different nuclear energy level. The elements in this series, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, and dubnium, are incredibly dense, often solid at room temperature, and possess unique nuclear properties. Some, like plutonium and uranium, are now vital in nuclear power generation and weaponry, demonstrating the profound impact these elements have had on our world. Despite their challenges in isolation and study, the lanthanides and actinides have become indispensable to many scientific and technological advancements. They're used in lasers, magnets, catalysts, and even in the production of high-strength alloys. Their unique properties, born from their complex electronic structures and inherent radioactivity, continue to fascinate and challenge scientists, further expanding our understanding of the building blocks of the universe. The story of these inner transition metals is a testament to the power of patient observation, meticulous experimentation, and the enduring human quest to unravel the secrets of matter. The periodic table, as we've explored, isn't simply a list of elements arranged alphabetically. It's a map, a remarkably detailed and elegant arrangement reflecting the fundamental nature of matter itself. And within this map, one particular property holds a surprisingly powerful key to understanding how atoms interact and form the vast array of compounds that make up our world: electronegativity. Electronegativity, at its core, describes the strength of an atom's attraction for electrons. It's a measure of how vigorously an atom pulls on those electrons within a chemical bond. Think of it like a tiny, invisible tug-of-war, constantly playing out between atoms. The larger the electronegativity value assigned to an element, the stronger its pull. Now, these electronegativity values aren't something you might intuitively grasp. They aren't measured in pounds or kilograms. Instead, they are determined experimentally through a combination of techniques. One primary method involves measuring the potential energy difference when an atom approaches another. When an atom with a high electronegativity gets near one with a low electronegativity, it's like a magnet. It's drawn towards the lower electronegativity atom, and that attraction is quantified. However, it's not just about the raw attraction. The electronegativity scale we use, often referred to as the Pauling scale, provides a standardized way to compare the relative strengths of these attractions. This scale runs from 0 to 4, with fluorine, the most electronegative element, holding the top spot at 4. Francium, on the far right of the table, is generally considered to be at 0, representing a very weak attraction for electrons. It's important to remember that this is a relative scale. It's about comparing the strengths of attraction between different elements, not about absolute force. The values assigned to each element are derived from the results of various experiments, including measuring the potential difference across the boundary of a liquid-liquid interface when an ionic compound is dissolved. The movement of ions creates a voltage, and this voltage is directly correlated with the electronegativity difference between the ions. Another approach utilizes the ionization energies of elements, looking at how easily an atom loses its outermost electrons. A smaller ionization energy often indicates a higher electronegativity because the atom is more eager to hold onto its electrons. The arrangement of the periodic table itself beautifully reflects trends in electronegativity. As you move from left to right across a period, electronegativity generally increases. This is because, as you add protons to the nucleus, the effective nuclear charge, the attraction between the nucleus and the valence electrons, becomes stronger. This stronger pull leads to a greater desire to hold onto electrons, resulting in higher electronegativity values. Furthermore, electronegativity increases as you move up a group. This trend is linked to the increasing number of electron shells. The valence electrons are located further away from the nucleus, making them more susceptible to being attracted by the positively charged nucleus. This distance also amplifies the effect of the nuclear charge, further strengthening the attraction. Now let's consider some specific examples. Sodium Na, a highly reactive alkali metal, has a very low electronegativity, around 0.93. This means it readily gives away its single valence electron to form a positive ion and bond with a more electronegative atom, such as chlorine. Chlorine, on the other hand, has an electronegativity of 3.16. This strong attraction pulls electrons towards itself, creating a covalent bond where the electrons are shared unequally, resulting in a polar bond. The difference in electronegativity is key to understanding the properties of sodium chloride, common table salt. Moving to oxygen O, with an electronegativity of 3.44, we see a significantly stronger pull. Oxygen is highly reactive and forms numerous covalent bonds, often with elements like hydrogen and carbon. The polar nature of these bonds profoundly impacts the properties of compounds like water, which is critical to almost every aspect of life. The concept of electronegativity extends beyond simply describing the attraction between atoms. It also helps explain the types of bonds that will form between them. If the electronegativity difference between two atoms is small, typically less than 1.7, the bond is considered nonpolar covalent, with an equal sharing of electrons. If the difference is significant, greater than 1.7, the bond is considered polar covalent, with one atom pulling the electrons more strongly than the other, resulting in a partial negative charge on one atom and a partial positive charge on the other. And of course, when the difference is large enough, we get ionic bonds, where electrons are completely transferred from one atom to another. Consider the bond between magnesium, Mg, and chlorine, Cl. Magnesium has an electronegativity of 1.31, while chlorine's is 3.16. This large difference leads to the formation of an ionic bond, creating magnesium chloride, MgCl2, a compound crucial in many industrial processes. Understanding electronegativity isn't just an academic exercise. It's a fundamental tool for predicting and explaining chemical behavior. It's a cornerstone of chemical bonding theory and plays a vital role in determining the properties of materials, from the hardness of a metal to the reactivity of a gas. It's a property that reveals a hidden order within the seemingly chaotic world of chemical reactions. It's a beautiful, powerful concept that connects the arrangement of the periodic table to the very nature of how atoms interact, constantly shaping the world around us. The atoms of every element, regardless of their position on the periodic table, are fundamentally built from a central nucleus surrounded by a swirling cloud of electrons. These electrons aren't just hanging around. They're in constant motion, buzzing with energy as they occupy specific, quantized energy levels around the nucleus. These energy levels, often visualized as shells or orbits, dictate how an atom interacts with other atoms and determines its chemical behavior. Each electron within a shell possesses a specific amount of energy. Now, let's consider what happens when we try to pull one of these electrons away from its designated spot. The force holding an electron within an atom, the attractive force between the negatively charged electron and the positively charged nucleus, isn't a static one. It's a dynamic interplay influenced by the electron's position within its energy level and the strength of the nucleus itself. As an electron moves further away from the nucleus, it's no longer as strongly held. It's like a child holding onto a balloon. The closer they are, the tighter their grip. But as they let go, the grip weakens considerably. This distance increases the electron's potential energy, and it takes energy to overcome this growing separation. This brings us to ionization energy. It's precisely the amount of energy required to remove an electron from a gaseous atom or ion. We're not talking about removing an electron from a molecule. That's a different process entirely. We're focusing on the fundamental removal of an electron from the atom itself. There are two primary types of ionization energy we need to understand. First, ionization energy, and second, ionization energy. First, ionization energy refers to the energy needed to remove the first electron from a neutral gaseous atom. It's the most demanding step, as it involves breaking the strongest bond between the electron and the nucleus. The ionization energy isn't constant across the periodic table. It changes dramatically depending on where the atom is located. Elements in the first column, the alkali metals like lithium, sodium, and potassium, exhibit exceptionally low first ionization energies. This is because they have only one electron in their outermost shell, which is relatively easy to remove. Just a small amount of energy, a few electron volts, is sufficient to knock that single electron away. This is why they're so reactive. They readily lose this outermost electron to achieve a more stable electron configuration. Moving across a period to the right, ionization energies generally increase. This is because the nuclear charge, the number of protons in the nucleus, steadily increases. With more protons, the nucleus becomes more positive, creating a stronger attraction for the electrons. It's like trying to pull a toy away from a very determined child. You need to apply more force. Now, let's consider what happens after we've removed the first electron. The atom is now a positively charged ion, and it's less stable than the neutral atom. The remaining electrons are held even more tightly. To remove a second electron, you need to supply even more energy than you did to remove the first. This second ionization energy is always higher than the first. The more electrons an atom has, the greater the attraction between them and the nucleus, and therefore the greater the energy needed to liberate another electron. The ionization energies aren't just about the number of electrons. They're also influenced by factors related to the atom's electronic configuration. Atoms with full outer shells, like noble gases, have very high ionization energies. They're already in a stable, low-energy state, and it takes a significant amount of energy to disrupt this stability. We can visualize this process using trends in the periodic table. You'll notice a distinct pattern. Ionization energies tend to increase as you move from left to right across a period, and as you move up a group. These trends aren't arbitrary. They're a direct consequence of the fundamental forces governing the interaction between electrons and the nucleus. Furthermore, understanding ionization energy is key to predicting the reactivity of elements. Elements with low ionization energies are typically highly reactive, as they readily lose electrons to form ions. Conversely, elements with high ionization energies tend to be less reactive, as they require a large amount of energy to lose electrons. The concept of ionization energy is also fundamental to understanding chemical bonding and the formation of ionic compounds. It's also important to remember that ionization energy is a measurable quantity, and we use experimental techniques, such as photoelectron spectroscopy, to determine these values for different elements. These measurements allow us to quantify the energy required to remove electrons and provide valuable insights into the electronic structure and reactivity of elements. The variations in ionization energy across the periodic table truly illuminate the intricate dance of electrons and nuclei that forms the foundation of chemistry. As we continue to explore the periodic table, remember that ionization energy is a crucial piece of the puzzle, offering a vital perspective on how atoms interact and how they build the world around us. It's a testament to the elegant and powerful principles that govern the behavior of matter at its most fundamental level. The world of atoms isn't a rigid, unchanging one. Each element, that fundamental building block of everything around us, possesses a surprisingly dynamic characteristic: its atomic radius. It's not simply a number. It's a measure of how far an atom's electrons extend outwards, representing the reach of that nucleus. Understanding atomic radius is key to unlocking many of the behaviors we observe in chemistry, from how elements interact to the structures they form. It's a concept that's evolved significantly over time, relying initially on clever, if somewhat indirect, methods and gradually incorporating more precise techniques. Early attempts to gauge atomic size were remarkably insightful, considering the limitations of the technology available. Scientists realized that the simple assumption of atoms being tiny, indivisible spheres was fundamentally flawed. If atoms were just miniature balls, they would inevitably overlap if packed tightly together, a fact that wasn't observed. This led to the concept of the atomic volume, a method pioneered by John Dalton in the early 1800s. Dalton proposed that if you could pack atoms perfectly, the volume occupied by a given mass of an element would be constant, regardless of the element itself. He demonstrated this by measuring the volume of a gas produced by reacting a known mass of a metal with an acid. By knowing the mass of the metal and the volume of the gas, he could calculate the atomic volume, the volume occupied by a single atom of that element. This was a groundbreaking approach, though it relied on the assumption of a perfect, regular arrangement of atoms, which rarely holds true in reality. The challenge then became refining this measurement. The early atomic volumes, calculated from gases like hydrogen and oxygen, indicated that atoms were significantly smaller than initially imagined. However, the method was plagued by uncertainties. The pressure and temperature of the gases used in the experiments could significantly influence the volume measurements, introducing considerable errors. Furthermore, the assumption of a perfect packing arrangement was again a critical point of vulnerability. If the atoms weren't arranged perfectly, the calculated volumes would be inaccurate. To address these issues, scientists began exploring alternative methods that didn't rely so heavily on gas measurements. One such approach involved studying the electrical conductivity of metals. It was observed that as the distance between atoms in a metal decreased, the metal's ability to conduct electricity increased. This phenomenon is connected to the movement of electrons through the material. A greater spacing between atoms allows for easier electron flow. Scientists like Samuel Morse meticulously measured the electrical resistance of various metals at different temperatures. The resistance of a material is inversely proportional to its volume. So by relating the resistance to the volume, they were able to estimate the size of the atoms involved. This method offered a more robust measurement, less susceptible to the inconsistencies of gas measurements. As technology advanced, more direct techniques were developed. X-ray diffraction, first utilized in the early 20th century, provided a revolutionary way to determine atomic radii. This technique exploits the wave-like nature of X-rays. When X-rays are shown on a crystalline solid, they are scattered by the atoms within the crystal lattice. The pattern of these scattered X-rays, the diffraction pattern, is unique to the arrangement of the atoms. By analyzing the angles and intensities of the diffracted beams, scientists could precisely determine the spacing between atoms, and therefore the atomic radius. This method essentially maps the three-dimensional structure of the atom. The data obtained through X-ray diffraction revealed a surprising trend. Atomic radii generally decrease as you move across a period, a row on the periodic table. This is because, within a single period, the number of protons in the nucleus increases, leading to a stronger pull on the electrons, causing them to be drawn closer to the nucleus. Furthermore, the number of electron shells surrounding the nucleus remains constant. The increased nuclear charge means the electrons are held more tightly, shrinking the radius. Conversely, as you move down a group, a column on the periodic table, the number of electron shells increases. This means the electrons are further away from the nucleus, leading to a larger atomic radius. The increased number of shells effectively dilutes the nuclear attraction, expanding the size of the atom. The outermost electrons, shielded by the inner shells, are less strongly held. It's important to note that atomic radius isn't a fixed value. It's a theoretical concept, an average size, reflecting the complexity of the atom's structure. The actual size of an atom is extremely difficult to define precisely because atoms don't have a clearly defined surface. However, the concept of atomic radius provides a valuable framework for understanding and predicting the behavior of elements and their compounds. It's a cornerstone of understanding the relationships that govern the entire periodic table, a testament to the elegant order embedded within the seemingly chaotic world of the elements. And as scientists continue to refine our measurement techniques, our understanding of this fundamental property of matter only grows more detailed and profound. The world of chemistry, at its most fundamental, is built on numbers. It's a world of incredibly small things, atoms, and understanding how much of those atoms are involved in any reaction or compound is absolutely crucial. Before we can talk about how elements interact, how they combine to create everything around us, or even predict the properties of a new material, we need a way to measure and compare the amounts of these elements. That's where molar mass comes in. It's a deceptively simple concept, but it's the cornerstone of much of our work with the periodic table. Molar mass isn't about measuring the physical size of an atom, though it's related to that in a way. Instead, it's a numerical representation of the mass of 1 mole of a specific element or compound. Now, what exactly is a mole? A mole is a unit of measurement, just like a gram or a liter. However, it's a very special kind of unit. It represents a precisely defined number of particles, 6.022 x 1023. That's a huge number, far larger than you can easily grasp. It's equal to the number of atoms in 12 grams of carbon-12, which is a standard reference used in defining the mole. Think of it like a chemist's dozen, but instead of 12 apples, it's 6.022 x 1023 atoms or molecules. Each element on the periodic table has a unique molar mass, expressed in grams per mole, g/mol. This value is found directly on the periodic table itself, listed below the element symbol. For example, the molar mass of hydrogen, H, is approximately 1.008 g/mol. This means that 1 mole of hydrogen atoms has a mass of 1.008 grams. Similarly, the molar mass of oxygen, O, is approximately 16 g/mol. This doesn't mean you'll find 16 grams of oxygen in a single atom, of course. It means that 1 mole of oxygen atoms, 6, 0, 22 x 10 23 of them, will weigh exactly 16 grams. The molar mass of a compound is calculated differently. It's the sum of the molar masses of all the atoms that make up that compound. Let's consider water, H2O. The molar mass of hydrogen, H, is 1.008 g/mol, and the molar mass of oxygen, O, is 16 g/mol. Therefore, the molar mass of H2O is 21.008 g/mol, plus 16 g/mol equals 18.016 g/mol. This means that 1 mole of water molecules will have a mass of 18.016 grams. Now, why is this so important? Molar mass allows us to convert between mass and moles, and between moles and number of particles. Let's say you have a sample of iron filings weighing 10 grams. You want to determine how many moles of iron are present. You would use the molar mass of iron, approximately 55.84 g/mol, to calculate the number of moles. The calculation is simple. Moles equals mass/molar mass. So moles of iron equals 10 g/55.84 g/mol, approximately 0.18 moles. This tells us that there are approximately 0.18 moles of iron in that 10-gram sample. Similarly, if you know the number of moles of a substance, you can calculate its mass. For example, if you have 0.5 moles of carbon, you can calculate its mass using the molar mass of carbon, 12.01 g/mol. Mass equals moles, molar mass equals 0.5 moles, 12.01 g/mol equals 6.005 grams. This is incredibly useful in laboratory settings, where precise measurements are paramount. Molar mass isn't just used for calculating the amount of individual elements or compounds. It's a fundamental tool in stoichiometry, the study of the quantitative relationships between reactants and products in chemical reactions. Balancing chemical equations relies heavily on molar mass to ensure that the number of atoms of each element is the same on both sides of the equation, maintaining mass conservation. Furthermore, molar mass plays a vital role in determining the theoretical yield of a reaction. By understanding the molar masses involved, chemists can predict how much product will be formed from a given amount of reactants, giving them a target to aim for and allowing them to optimize their processes. It's a cornerstone for understanding how reactions work and how to control them. The periodic table itself is organized in part due to these molar mass relationships. Elements are grouped together based on their similar chemical properties, which often correlate with trends in their molar masses. This interconnectedness highlights the underlying numerical foundation of chemistry. Ultimately, Molar mass provides a convenient and consistent way to relate the microscopic world of atoms and molecules to the macroscopic world of measurable quantities: mass, volume, and concentration. It's a deceptively simple concept with profound implications for understanding and manipulating the chemical world around us. It truly is a silent, powerful guide within the organized structure of the periodic table. The periodic table, a seemingly ordered grid of elements, holds a secret far more intricate than simple arrangement. It's not just about the weight of an atom or its tendency to gain or lose electrons. At the heart of the table's surprising diversity lies a concept called isotopes. Isotopes are like subtly different versions of the same element, all sharing the same number of protons. That's the key characteristic that defines an element. But they differ in the number of neutrons residing within their nucleus. Consider hydrogen, a remarkably simple element. You might learn that it always has one proton. That's what makes it hydrogen. Now, imagine a hydrogen atom with one proton and one neutron in its nucleus. This is called protium, and it's the most common form of hydrogen. It's incredibly stable, making up roughly 90% of all hydrogen atoms on Earth. But the story doesn't end there. Another hydrogen atom might possess one proton and two neutrons. This is called deuterium, sometimes referred to as heavy hydrogen. The extra neutron adds a little mass and drastically alters its properties. Deuterium is much less abundant than protium, and it's one of the few naturally occurring isotopes that has a different chemical behavior due to its heavier mass. It participates in a unique type of bonding, and it's even used in specialized research. Then there's tritium, an isotope of hydrogen with one proton and two neutrons. It's far rarer, and it's radioactive, meaning its nucleus is unstable and spontaneously decays, emitting radiation. This radioactivity makes it incredibly useful in tracing processes. Think of tracking water molecules through a biological system. For example, the different rates at which these isotopes decay contribute to radioactive dating methods used to determine the age of ancient rocks and fossils. The existence of isotopes isn't an anomaly. It's a fundamental aspect of atomic structure. The nucleus, that incredibly dense core of an atom, isn't just a fixed unit. The number of neutrons can vary, adding a layer of complexity to the element's behavior. This variation in mass, even though the number of protons remains constant, has a significant impact on how elements interact with each other. The mass of an atom is primarily determined by the number of protons and neutrons. Elements with heavier isotopes tend to have slightly different chemical properties. While the differences are often subtle, they're measurable and provide valuable information. For instance, the rate at which an isotope decays, its half-life, is a key factor in understanding nuclear reactions and the evolution of the universe. Now let's consider a slightly more complex example: carbon. Carbon-12, carbon-13, and carbon-14 are all isotopes of the same element, carbon. Carbon-12 is the most abundant and stable form, playing a crucial role in the majority of chemical reactions. Carbon-13 is less common and is often used as a tracer in biological studies, allowing scientists to track the movement of carbon within living organisms. but it's carbon-14 that's perhaps most famous. Carbon-14 is a radioactive isotope that's constantly being produced in the upper atmosphere through the interaction of cosmic rays with nitrogen. It's then incorporated into living organisms as they consume plants and animals, maintaining a constant ratio of carbon-14 to carbon-12. When an organism dies, this incorporation stops, and the carbon-14 begins to decay at a known rate. By measuring the amount of remaining carbon-14, scientists can calculate how long ago the organism died, a technique known as radiocarbon dating. The concept of isotopes isn't limited to just hydrogen and carbon. Every element, from oxygen to iron to gold, exists in multiple isotopic forms, each with a different number of neutrons. The abundance of each isotope varies depending on the element and the natural conditions surrounding it. Some isotopes are extremely rare, while others are relatively common. These variations contribute to the overall diversity of the periodic table. Furthermore, scientists can create isotopes in laboratories, deliberately altering the number of neutrons in an element's nucleus through nuclear reactions. These artificially produced isotopes are invaluable tools for research in fields ranging from medicine to materials science. For example, radioactive isotopes are used in cancer treatment, allowing doctors to target and destroy cancerous cells with greater precision. The exploration of isotopes has expanded our understanding of the universe itself. The ratios of different isotopes in ancient meteorites provide clues about the formation of the solar system, and the distribution of isotopes in stars helps astronomers study stellar evolution. It's a fascinating field, illustrating how seemingly small differences within the building blocks of matter can have profound consequences. The periodic table, therefore, isn't just a list of elements. It's a detailed map of the potential variations within those elements. It's a testament to the intricate and beautiful complexity hidden within the very core of our world. It's a reminder that even the most fundamental components of reality hold remarkable surprises. The study of isotopes continues to unlock new secrets, constantly reshaping our understanding of the universe and our place within it. The universe whispers secrets in the heart of certain elements, secrets held not in their shape or size, but in the restless energy that pulses within their very nuclei. These elements, often found deep within the Earth's crust and mantle, are radioactive, meaning they are inherently unstable. Their existence is a delicate dance of particles, a constant shedding of energy in the form of radiation. This isn't a destructive process in the immediate sense. Rather, it's a transformation, a slow and methodical reshaping of the element itself. We'll delve into the fascinating world of uranium and thorium, two of the most prominent examples of these naturally occurring radioactive elements. Uranium, represented by the symbol U on the periodic table, is particularly noteworthy due to its significance in nuclear energy. It's a heavy metal, quite dense, and exists in several forms or isotopes, each with a slightly different number of neutrons in its nucleus. The most common isotope, uranium-238, is particularly intriguing because it's incredibly stable. It takes an astonishingly long time, approximately 4.5 billion years, for a single atom of it to decay. However, not all uranium isotopes are so patient. Uranium, a smaller, lighter isotope, is the one that's readily usable in nuclear reactors. It's far more likely to undergo radioactive decay, initiating a chain reaction that produces a controlled release of energy. The process of decay begins with alpha decay. An alpha particle is essentially a helium nucleus, two protons and two neutrons bundled together. When a uranium-235 atom undergoes alpha decay, it emits this particle. The nucleus shrinks, becoming thorium-230, and releases a tremendous amount of energy in the form of kinetic energy for the emitted alpha particle and gamma radiation. Gamma radiation, unlike alpha particles, is pure energy. It's a high-energy electromagnetic wave. It doesn't carry a charge and therefore can pass through most materials relatively unimpeded. The decay of uranium-235, and indeed all alpha emitters, is a slow, gradual transformation. It's like watching a carefully constructed tower of blocks slowly crumble, piece by piece, until only the foundations remain. Thorium, symbolized as Th on the periodic table, presents a different, though equally compelling, story. Unlike uranium, thorium is surprisingly stable. Thorium, the most abundant isotope, boasts an incredibly long half-life, approximately 14.05 billion years. That's far longer than the age of the universe itself. Despite this immense stability, thorium-232 is still radioactive and undergoes a series of decay processes, a cascade of transformations that ultimately lead to stable lead. This decay process isn't a single, dramatic event like the alpha decay of uranium-235. It's a more complex, multi-stage process. The initial decay of thorium-232 begins with beta decay. A beta particle is an electron, one of the fundamental constituents of an atom. In this case, the nucleus emits an electron, transforming into protactinium-238. Protactinium is itself a radioactive element, and this step marks the beginning of a long chain of beta decays. Each beta decay step reduces the atomic mass of the nucleus by 2 and changes the element it's emitting from. This continues for a remarkable length of time, transforming into several different elements before finally settling into a stable lead isotope, lead-206. This entire chain, from thorium-232 to lead-206, is estimated to take around 8160 million years to complete. It's an astonishingly slow process, a testament to the inherent stability of the thorium nucleus. It's important to understand that the radiation emitted during these decays isn't harmful in small amounts. It's only when a significant concentration of radioactive material is present that the effects become noticeable. Furthermore, the radiation isn't a destructive force in itself. It's the energy carried by the emitted particles that can cause damage. The presence of uranium and thorium in the Earth's crust played a crucial role in the planet's early history. These elements were among the first to form after the Big Bang, and their radioactive decay released immense amounts of heat, driving geological processes like volcanism and plate tectonics. Scientists can even use the decay rates of uranium and thorium to determine the age of rocks and minerals, a technique called radiometric dating. The longer the half-life of an element, the more precise the dating can be. Consider the geological timescales involved. The age of the Earth is approximately 4.54 billion years old. The half-life of uranium-238 is 4.5 billion years. This means that nearly all of the uranium-238 that was ever present on Earth has already decayed, leaving behind a small amount of its daughter products. The same principle applies to thorium-232, though its much longer half-life means that a considerably larger proportion of it has also decayed. These elements are constantly transforming, playing a silent, fundamental role in shaping our planet. They are more than just symbols on a periodic table. They are witnesses to the vastness of time, silently recounting the history of the Earth. Studying them gives us insights into Earth's formation and evolution. The study of radioactive elements like uranium and thorium continues to provide valuable information about the universe. It's a field that combines physics, chemistry, and geology, and it remains a vital area of scientific investigation. As we delve deeper into the secrets held within their nuclei, we uncover a fascinating story of transformation, decay, and the enduring power of the elements. It's a reminder that even the seemingly stable things in the universe are, at their core, in a state of constant change. The periodic table isn't simply a neat arrangement of elements, like colorful building blocks arranged by size. It's something far more profound, a remarkably accurate model that reveals the underlying reasons why elements interact with each other, predicting how they'll react under specific conditions. It's like a cosmic choreographer, arranging elements in a way that anticipates their dances, their chemical reactions. The table's order isn't arbitrary. It's built on fundamental properties of the atoms themselves, particularly their electron configurations. At the heart of this predictive power lies the concept of valence electrons. These are the electrons residing in the outermost shell of an atom, the ones most involved in forming chemical bonds. The number of valence electrons an atom possesses dramatically influences its behavior. Atoms want to achieve a stable state, often resembling the electron configuration of a noble gas, a full outer shell. This drive for stability is what fuels most chemical reactions. Elements in the same vertical column, called a group, share similar valence electron configurations. Consequently, they tend to react in similar ways. For example, all the alkali metals, lithium, sodium, potassium, belong to group 1. They all have a single valence electron, making them incredibly reactive. They readily lose this single electron to form positively charged ions, readily participating in reactions that involve forming ionic bonds. Sodium, in particular, is famous for its reaction with chlorine, a halogen in group 17, creating table salt, sodium chloride, a very stable compound. The table visually communicates this tendency. Elements in the same group have similar reactivity patterns. Moving across a period horizontally reveals a different kind of reactivity trend. As you move from left to right, the number of valence electrons increases. This has a significant impact. Elements like hydrogen, located on the far left, have only one electron and are relatively unreactive under normal conditions. However, as you move towards the right, elements like oxygen, with 6 valence electrons, become increasingly reactive. Oxygen's strong tendency to gain 2 electrons to complete its outer shell drives many reactions, such as combustion, the burning process. The table demonstrates this pattern clearly. Reactivity changes steadily as you traverse a period. The periodic table also helps us predict the type of bonds an element is likely to form. Elements with nearly full outer shells, like oxygen and fluorine, are strongly inclined to form covalent bonds, sharing electrons to achieve stability. Conversely, elements with only 1 or 2 valence electrons, like metals in group 1, favor ionic bonding by donating their electrons. The table acts as a guide, hinting at the bonding possibilities based on the electronic makeup of each element. Furthermore, the table allows us to predict the stoichiometry, the ratios in which elements combine in chemical reactions. By analyzing the electronic configurations of the reactants, chemists can anticipate the number of molecules or formula units that will be produced. Consider the reaction between hydrogen and oxygen, a reaction that creates water. The table, by showing hydrogen's single electron and oxygen's need for 2, immediately suggests the 2:1 ratio, 2 hydrogen atoms combining with 1 oxygen atom. This isn't guesswork. It's a prediction based on the fundamental electronic structure of the involved elements. The periodic table isn't perfect, of course. There are always exceptions to the rules, particularly with transition metals, where the arrangement of electrons within the inner shells can complicate the picture. But for the vast majority of elements, the periodic table provides a remarkably accurate framework for understanding and predicting chemical behavior. It's a powerful tool for chemists, allowing them to design and control reactions, synthesize new compounds, and ultimately unlock the secrets of the materials that make up our world. Consider the reaction between iron and chlorine. Iron, a transition metal, has a complex electron configuration, but the table still offers insights. The predictable formation of iron chloride with its characteristic properties isn't a surprise when viewed through the lens of the periodic table's predictive power. The table illustrates that even within this complex metal, there's a systematic relationship between electronic structure and reactivity. The beauty of the periodic table lies in its ability to distill complex quantum mechanical properties, the behavior of electrons at the atomic level, into a simple, visually accessible model. It's a testament to human ingenuity and our ability to understand and represent the fundamental forces that govern the universe. As you continue to explore the periodic table, remember that it's not just a chart. It's a map guiding you through the fascinating world of chemical reactivity, a world of predictable dances and transformative reactions. It's a key to unlocking a deep understanding of the world around us, one element at a time. The air around a sodium atom is, to put it mildly, restless. It's a restless energy, a constant yearning to share. This behavior is at the very heart of what makes alkali metals so remarkable, and it's a characteristic dictated by their electron configuration. These elements, lithium, sodium, potassium, rubidium, and cesium, sit comfortably at the far left of the periodic table, a region defined by having only one electron in their outermost shell. This single electron is incredibly eager to abandon its bond with the sodium atom, a desire fueled by the atom's inherent tendency to achieve a stable, full outer shell, a noble gas configuration. The reactivity of alkali metals isn't just a casual preference, it's a fiercely competitive drive. When exposed to water, for example, the reaction is immediate and dramatic. A small piece of sodium, shimmering silver in its pure state, will visibly disappear in a fizzing, popping display. This isn't simply dissolving, it's a rapid chemical transformation. The sodium atom violently donates its single valence electron to the water molecule. This donation causes the water molecule to split, creating hydrogen gas, which you'll notice as the bubbles, and a powerfully alkaline solution of sodium hydroxide. The energy released during this process is what manifests as the heat and light we observe. The reaction isn't just about sodium, it's about the principle of electron transfer. Each alkali metal behaves similarly, though the vigor of the reaction, the speed and intensity of the fizzing, varies slightly depending on its size. Larger alkali metals, like cesium, tend to react with water more readily than smaller ones like lithium. This is because the greater the distance between the nucleus and the outermost electron, the weaker the attraction holding the electron in place, and therefore the more easily it can be lost. Sodium, in particular, is a cornerstone of countless industrial processes. Its reactivity isn't just a scientific curiosity, it's a carefully controlled and immensely useful property. Sodium metal is used in the production of sodium salts, sodium chloride table salt, sodium carbonate soda ash, and many others. These salts play vital roles in everything from food preservation to glass manufacturing. Lithium, though less reactive than sodium, possesses a unique set of properties that have led to its widespread adoption in a remarkably diverse range of applications. It's significantly lighter, and its charge, a single positive charge, gives it a particularly useful characteristic. It can be easily ionized. When lithium atoms gain energy, such as through heating or exposure to light, their electrons become detached, creating a stream of lithium ions. This is the basis for lithium-ion batteries, which are now ubiquitous in smartphones, laptops, electric vehicles, and a growing array of other electronic devices. The energy stored within these batteries is created by carefully controlling the movement of lithium ions between a positive electrode cathode and a negative electrode anode. The materials used in the electrodes are specifically designed to facilitate this movement, and the electrolyte, a liquid or gel that conducts the ions, allows for a smooth and efficient flow. Lithium-ion batteries are considered a significant advancement in energy storage due to their high power density, long lifespan, and relatively low self-discharge rate. Beyond batteries, lithium compounds are also used in lubricants, ceramics, and pharmaceuticals. The pharmaceutical industry frequently employs lithium salts as mood stabilizers in treating bipolar disorder. The precise mechanism of action isn't fully understood, but it's believed to involve the influence of lithium ions on neuronal activity within the brain. The ionic character of alkali metals is crucial to their behavior. Because they readily donate their single electron, they form strong, positively charged ions, Na plus and Li plus. For example, these ions are attracted to negatively charged ions, anions, and to neutral molecules with partial negative charges. This attraction is what drives many of the reactions that alkali metals participate in, and is responsible for their ability to dissolve in polar solvents like water and alcohol. Interestingly, the properties of lithium extend beyond its ionic character. At extremely low temperatures, colder than even the lowest temperatures achievable in laboratories, lithium exhibits a fascinating phenomenon known as superconductivity. Below a critical temperature, lithium loses all resistance to electrical current, meaning electricity can flow through it indefinitely without any loss of energy. This property is still under intense study, as scientists explore ways to harness this remarkable characteristic for applications such as lossless power transmission and high-speed electronics. The exploration of alkali metals continues to reveal new insights into the fundamental nature of matter and opens doors to innovative technologies. The simple act of a single electron leaving a sodium or lithium atom holds the key to a world of possibilities, demonstrating that even the smallest component of an element can have a profound impact on our lives and our understanding of the universe. The periodic table, a vast and shimmering landscape of elements, continues to reveal its secrets. We've just journeyed through the realm of the alkali metals, sodium and lithium, learning about their astonishing reactivity and the way they readily give up electrons. But there's another group, nestled to the right of the alkali metals, that possesses a unique character, a slightly calmer energy, and a vital role in countless aspects of our world: the alkaline earth metals. These are magnesium and calcium, and their story is one of surprisingly strong bonds and essential contributions. Magnesium, with its atomic number 12, is a silvery white metal that appears almost luminous in the light. It's quite malleable, meaning you can easily shape it into wires or sheets, and it's also a good conductor of electricity, though not as conductive as copper. Its most remarkable property, however, is its ability to burn with a brilliant, almost ethereal white light when heated. This isn't a dangerous flame, but rather a captivating display of energy. Magnesium's density is also noteworthy. It's lighter than aluminum, making it an excellent choice for applications where weight reduction is crucial. Interestingly, magnesium combines with oxygen to form magnesium oxide, MgO, a compound that's incredibly stable and resists corrosion, a property that makes it valuable in protecting other metals. Calcium, the fifth element in this group, number 20, tells a different, yet equally important story. Unlike magnesium's silvery appearance, calcium is a chalky white solid at room temperature. It's a much harder metal, requiring more force to bend or shape. Calcium's significance isn't primarily found in its own physical properties, but rather in its abundant role within living organisms. It's a fundamental component of bones and teeth, providing them with their strength and rigidity. This is due to its ability to form strong, rigid structures with other calcium ions, creating a remarkably robust framework. Beyond bone and teeth, calcium ions are vital for countless cellular processes, playing a role in muscle contraction, nerve transmission, and blood clotting. The reactivity of magnesium and calcium is noticeably less vigorous than that of the alkali metals. They still readily react with water, albeit more slowly, producing hydrogen gas and an alkaline solution, magnesium hydroxide and calcium hydroxide, respectively. The reaction with water is a classic example of a single displacement reaction, where magnesium or calcium takes the place of hydrogen. This is why you'll often see magnesium or calcium presented as a protective coating on other metals, preventing them from reacting with atmospheric oxygen and water. This protective action is incredibly important in industries like aluminum production, where magnesium is used to prevent the aluminum from corroding during the smelting process. Calcium's reaction with water is particularly interesting because it forms calcium hydroxide, Ca(O2), commonly known as slaked lime. Slaked lime has a wide range of applications. It's used to neutralize acidic soils in agriculture, improving their suitability for plant growth. It's also a key ingredient in mortar and cement, reacting with water and other materials to create strong, durable building materials. The process of making cement relies heavily on the chemical reactions involving calcium compounds, a testament to the element's foundational role in construction. Both magnesium and calcium are crucial in the production of alloys, combinations of metals designed to have enhanced properties. For instance, magnesium is frequently alloyed with aluminum to create a lightweight, strong material used in aerospace applications and automotive parts. These alloys leverage the combination of the metal's properties, magnesium's lightness and aluminum's strength, to achieve optimal performance. Similarly, calcium compounds are employed in the production of ceramics and refractories, materials that resist high temperatures and chemical attack. The industrial applications of these alkaline earth metals extend far beyond simple alloys. Magnesium is used in the manufacture of spark plugs, which ignite the air-fuel mixture in a gasoline engine, capitalizing on its ability to burn intensely. Calcium compounds are employed in the production of paper, where they act as a sizing agent, controlling the absorbency of the paper. Even in the realm of medicine, calcium supplements are widely used to treat conditions such as osteoporosis, strengthening bones and preventing fractures. The periodic table, in its careful arrangement, highlights the relationships between these elements. Magnesium and calcium, though less reactive than their alkali metal cousins, share similarities in their electronic structure. They both have 2 electrons in their outermost shell, which contributes to their similar chemical behavior. However, the increasing number of electrons adds to their stability and influences their reactivity patterns. It's a beautiful illustration of how the periodic table organizes not just by atomic number, but also by the subtle nuances of an element's behavior. As we conclude our journey through the alkaline earth metals, remember that magnesium and calcium are far more than just elements on a chart. They are fundamental components of our world, quietly but powerfully shaping our environment, our health, and countless technological innovations. Their story is a continuing one, a testament to the enduring importance of these often overlooked elements in the grand scheme of the periodic table. The periodic table, a vast and intricate landscape of elements, isn't just a chart. It's a story of how atoms interact, how they bond, and how those bonds create the incredible diversity of the world around us. We've spent time exploring the behaviors of alkali metals, a dazzling group known for their eagerness to relinquish electrons, and alkaline earth metals, whose stability and influence are woven into the very fabric of our planet. But there remains one element, arguably the most fundamental, the most abundant, and yet often the most surprisingly complex: hydrogen. Hydrogen sits in the first column of the periodic table, alongside the alkali metals, a historical accident of naming that belies its profoundly different chemistry. The alkali metals, lithium, sodium, potassium, and their relatives, are all fiercely reactive, eager to donate their single electron to form positive ions. They're like boisterous children, constantly seeking connection. Hydrogen, however, behaves in a far more nuanced way. While it too can lose its electron to form a positive ion, the hydrogen ion, or proton, it's far less inclined to do so permanently. This makes hydrogen's chemistry uniquely fascinating and frequently misunderstood. The key to understanding hydrogen's behavior lies in its small size and low electronegativity, a measure of an atom's ability to attract electrons in a chemical bond. Because it's so small, hydrogen's nucleus is very close to its single electron. This proximity creates a strong attractive force, holding the electron tightly. As a result, hydrogen doesn't readily donate electrons to form ionic bonds the way the alkali metals do. Instead, it tends to share electrons, forming covalent bonds. This sharing leads to the creation of molecules with incredibly diverse properties, ranging from the simplest molecular hydrogen, H2, to extraordinarily complex compounds. Molecular hydrogen itself is a colorless, odorless gas at room temperature. It's remarkably stable, and its diatomic form, H2, is exceptionally unreactive under normal conditions. This stability is what allows it to exist abundantly in the universe, forming a significant portion of interstellar gas clouds. But when conditions change, when heat, pressure, or a catalyst are introduced, the possibilities explode. Hydrogen's ability to form covalent bonds with other elements creates a staggering array of compounds, far more varied than one might initially expect. Consider water, perhaps the most familiar compound of hydrogen. Two hydrogen atoms, each sharing their electrons with one oxygen atom, create a remarkably stable molecule. Water's polarity, stemming from this shared electron distribution, is responsible for its incredible properties. Its ability to dissolve so many substances, its high surface tension, and its crucial role in sustaining life. It's a beautiful example of how seemingly simple hydrogen can contribute to something so complex and essential. However, hydrogen's chemical versatility extends far beyond water. It forms compounds with nearly every other element in the periodic table. With fluorine, it creates hydrogen fluoride HF, a highly corrosive acid. With chlorine, it produces hydrochloric acid HCl, another powerful acid. With nitrogen, it forms ammonia NH3, a vital component of fertilizers. With oxygen, beyond water, it produces hydrogen peroxide H2O2, a powerful oxidizing agent used in bleaching and disinfectants. The chemistry of hydrogen also plays a critical role in the formation of organic molecules, the building blocks of life. Carbon, famously, forms the backbone of countless organic compounds, but hydrogen is almost always present, providing the framework and influencing the properties of these molecules. From simple hydrocarbons like methane, CH4, a primary component of natural gas, to the complex sugars and proteins that make up living organisms, hydrogen is inextricably linked. Furthermore, hydrogen is involved in a remarkable number of industrial processes. It's used in the production of ammonia, a key ingredient in fertilizers, fueling the growth of crops worldwide. It's employed in the refining of petroleum, removing sulfur and other impurities. And increasingly, hydrogen is being explored as a clean energy carrier, with the potential to power vehicles and generate electricity without producing harmful emissions. The behavior of hydrogen in metallic alloys is particularly interesting. When added to metals like iron, it creates incredibly strong and durable materials, high-strength steels. These steels are used in construction, automotive manufacturing, and countless other applications. The interaction between hydrogen and the metal lattice creates a complex network of hydrogen atoms, significantly enhancing the material's strength and toughness. Despite its fundamental importance, hydrogen's chemistry continues to be a subject of ongoing research. Scientists are constantly exploring new ways to utilize hydrogen as a clean energy source and developing innovative applications for hydrogen-based materials. The interplay of its unique electronic structure and its ability to form diverse bonds ensures that hydrogen will continue to fascinate and inspire scientific exploration for generations to come. It's a testament to the fact that even the simplest element can hold the key to some of the most complex and important phenomena in the universe. The periodic table, a map of the elements, isn't just a beautiful arrangement of symbols and numbers. It's a cornerstone of modern chemistry and technology. Its influence stretches far beyond simply predicting how elements will react. It's fundamentally reshaped our approaches to creating new materials and driving incredibly efficient chemical processes. We've moved beyond simply understanding the why of reactions, and now we can routinely control them. And the periodic table provides the framework for this control. A core area of this impact lies in the field of catalysis, where the table's organization reveals incredibly powerful strategies. Consider the development of petroleum refining. Before the 20th century, crude oil was a messy, unusable sludge. It contained a bewildering mixture of hydrocarbons, long chains of carbon and hydrogen, and separating them into useful products like gasoline, kerosene, and lubricating oils was a haphazard, low-yield process. Scientists began to look to the periodic table for clues. They realized that certain metals, particularly transition metals like platinum, palladium, and nickel, could dramatically accelerate specific reactions within this complex mixture. These metals act as catalysts, dramatically speeding up the breakdown and rearrangement of the hydrocarbons without being consumed themselves. The arrangement of these metals on the periodic table, particularly the transition metals and those in Group 8, provides a logical basis for their effectiveness in promoting specific types of bond breaking and formation, the very processes that transform crude oil into valuable fuels. The careful selection of catalysts, guided by understanding their electronic structure and position on the table, has revolutionized the industry, enabling the production of vast quantities of fuels and chemicals. But catalysis isn't confined to the petroleum industry. It's pervasive in countless other processes. The Haber-Bosch process, developed in the early 20th century, is perhaps one of the most impactful examples. This process, using iron catalysts, allows for the industrial-scale synthesis of ammonia from nitrogen and hydrogen. Ammonia is, of course, a vital ingredient in fertilizers, and this discovery fundamentally changed agriculture, enabling dramatically increased crop yields and consequently feeding a much larger global population. The design of the catalyst, the precise composition and structure, directly relates to the ease with which nitrogen molecules can be broken apart and combined to form ammonia, a process strongly influenced by the electronic properties of the metal catalyst. The table guides scientists in tailoring these properties to optimize the reaction. The impact extends significantly into materials science. The periodic table isn't just a list of elements. It's a guide to creating materials with precisely tailored properties. Consider the creation of high-strength alloys. Alloying, the mixing of two or more metals, is a common technique, but simply combining metals doesn't always produce a superior material. The arrangement of elements on the periodic table allows scientists to predict and control the resulting properties. For instance, adding small amounts of elements like silicon to aluminum creates aluminum alloys with significantly increased strength and corrosion resistance. The strategic selection of these elements, based on their positions within the table, influences the way the metal atoms arrange themselves, creating a more ordered and robust structure. Similarly, the creation of semiconductors, the backbone of modern electronics, relies heavily on the periodic table. Elements like silicon and germanium, located near the center of the table, are essential components of integrated circuits, their electronic properties precisely controlled through doping, intentionally introducing impurities to alter the material's conductivity. Moving beyond traditional alloys, the periodic table is instrumental in the development of nanomaterials. The ability to manipulate individual atoms and molecules, guided by periodic trends like electronegativity and atomic radius, has enabled the creation of materials with entirely new properties at the nanoscale. Carbon nanotubes, incredibly strong and lightweight cylinders of carbon atoms arranged in a hexagonal lattice, a pattern directly derived from the table's periodicity, are a prime example. Similarly, graphene, a single layer of carbon atoms arranged in a similar hexagonal lattice, exhibits extraordinary strength, conductivity, and impermeability, properties that are fundamentally linked to its structure, which is, of course, dictated by the arrangement of atoms outlined by the periodic table. Furthermore, the periodic table's understanding of bonding principles, ionic, covalent, and metallic, directly informs the design of new materials. By manipulating the electronic structure of materials according to trends on the table, scientists can control how they interact with light, heat, and other materials. This is vital in areas such as solar cell technology, where the precise arrangement of atoms within a semiconductor influences its ability to convert sunlight into electricity, and in the development of advanced coatings for corrosion resistance based on materials with tailored electronic properties. The table's influence is not just in the creation of materials, it's in the control, the optimization, and the understanding of how materials will behave in complex environments. It's a framework for innovation, constantly pushing the boundaries of what's possible. The ongoing research into new materials and the relentless advancements in catalysis are inextricably linked to the fundamental principles revealed by the organization of the periodic table. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. The elements have revealed their secrets, their dance of creation now a distant echo. Let your thoughts drift, calm and unhurried like atoms themselves, settling into stillness.